All right, in this next lesson, what I want to do is I want to give you guys a basic understanding of cryptography, and we're going to walk through a little bit of the history of where cryptography actually came from. So, once again, this is Tommy Cooksey from No Magic, Just Logic. I'm putting together a series to give everyone really just a better understanding of digital currency, blockchain, and digital ledger technology so that we all can see where we can utilize this technology and take advantage of it in our real-world environment and why it's going to be so useful as Web 3.0 catches traction and we start to see the new inventions of some of the new technologies that we come to see every day. So anyway, I'm just hoping to prepare people for a lot of the new things that are coming and some of the new, what I would consider Web 3.0 or the new industrial revolution or whatever you guys want to call this. All right, so we're going to get a basic understanding of cryptography. So again, my name's Tommy Cooksey. I love to come out and talk to you if you ever want to learn more about cryptography or if you want to learn more about anything that I talk about in these lessons. Please feel free to reach out to me. I do these lessons for free, so if you'd like to make donations, there's my Ethereum wallet. I'd appreciate any tokens or any type of ERC20, 721, whatever kind of tokens you might have that you might like to donate to the cause. My name again is Tommy Cooksey. There's my email address if you'd like to reach out to me to speak to your meetup group, college group, school, class, retirees. You want to learn how to do trading, whatever it is that you want to learn about in this industry. I'd love to come talk to you. All right, so what is cryptography? The term cryptography is really just the art of writing and solving codes. So many times when I think of cryptography and I think of when I first got introduced to cryptography, I think back to kind of when I was working on puzzles with my mom. My mom was a puzzle person. She always had puzzles on the kitchen table. And so I kind of grew up around puzzle books, puzzles, always around puzzles. And learning how to solve different problems. And so I think it put me in a good position to understand cryptography. So with that being said, I think that many of us see cryptography as some type of mysterious thing, but the reality is it's just simply the art of taking information that is really unreadable and then turning it into being readable again, or taking information that's easily readable, making it unreadable, sending it across an area where people that will look at it and just think, wow, that's garbage. But then when it gets to the individual that it's required to be read, they can make sense of it. So in essence, that's what we call a cipher and a decipher, or scrambling of information and unscrambling of information. And so that's what we're doing whenever we think about cryptography. We're simply just ciphering and unciphering information so that it can be read, and it can be only read by the individuals that it's intended for. So we're going to look at some of the ways that this has been used throughout history. We're going to look at some of the individuals involved. I always like to talk about that, the history and the individuals that have kind of helped to create the industry we call cryptography and cryptology. And then we're going to kind of discuss some of the modern cryptography techniques that are used today in order to secure things. So in essence, the important thing to remember is we want to create secure communication over an unsecure media. And so if you want to look at one of my earlier videos, I talk about the Byzantine general problem, and that's where we're kind of talking about using some type of a messaging protocol to ensure that we fix somebody being a bad actor. So we'll talk more about that in some other videos probably. All right, so let's go ahead and think about one of the first times we ever saw cryptography being used. And I think this is a really cool time. It was when Julius Caesar was wanting to do secure communication between his generals and also between banks and things like that. And so what they did is they decided to create a method for messaging that would take the standard message that would normally be delivered if intercepted, could easily be decoded. They wanted to take that message and they wanted to make it so that it wouldn't easily be read. And so how they decided to do this is they simply came up with what was called an alphabet shift cipher. And all that did is it simply took a particular set of numbers. So maybe you said the first word might be 3, the second word might be 5, the third word might be 6. So 3, 5, 6 was the number pattern, and there was 3 words. So the first word you would shift 3 spaces, the second word 5 spaces, and the third word 6 spaces. Something along those lines. But anyway, if you did something like this, it would be very simple. So let me explain to you what I mean by 6 places and what I mean by this. If I was just saying hello world and I was doing like a 3-space shift, well, the H would become a K, right? So H I J K, right? And then so that's what we're saying, right? So for the 3, and then you could do that for the first word, then the second word, W, X, Y, Z. So then you got your 3 there. So but you could change this and you could say, and instead of just saying 3 for both words, you could say 3, 5, and then the second word would be instead of 3, you could say it 5, and then anyway, you guys get the idea. But that's very weak. It's kind of it's just like me coming up with this is how I'm going to do it. I'm going to tell you how I'm going to do it. And then the alphabet, right? So you don't really need to rewrite that. You just know what it is. And so then you can just use that to figure out what we're going to do, right? And so you could use maybe a newspaper. You could do a lot of cool things like this when you start thinking about how you want to do like ciphering, right? So you want to create an encrypted message, right? So you want to do something. So that was a very weak usage of valiant effort, Julius Caesar, but very weak use of encryption. I'm sure some of the Byzantine generals that he was fighting against probably were able to crack some of those alphabet shift ciphers, because it's not very many permutations possible when we think about that type of cryptography. So when we think about that type of cryptography, really there's only, in our current alphabet, there's only 20-ish or so permutations, depending on what your language is. So anyway, there you go. That's alphabet shift cipher. So let's fast forward in cryptography. So look, what did we learn there real quick? We learned basically what cryptography is. We talked a little bit about cryptology, kind of as a science of cryptography. And then we also talked about what a cipher is and then a decipher, right? And so what they're used for, and then kind of the simple usage of them. And so to take that one step further of what we kind of learned, we learned that the permutations, or there was only kind of 20 different different ways that we could kind of hash this stuff up, or mix this stuff up, I should say. And so when you think of hash, when you think of hash, you're mixing something, right? So that keep that in mind, right? So if you eat something like corned beef hash, right? It's got potatoes and corned beef and stuff like that in it. It's all mixed together. Well, that's a hash, right? And so just kind of put that in your back pocket for a second, because we're going to talk about that in a second. All right, so the German Enigma machine. So let's talk about this for a minute. The Enigma machine was very interesting because what it did is, remember those permutations that we talked about? It allowed the sender and the recipient to kind of type their message through this machine right here. And I kind of described that here, but if you want to read through that, you can. But basically all they're doing is they're typing this stuff in this machine, and as long as the settings on the machine are the same on this machine as the person that types in the whatever comes out of the machine, on the recipient side, so this is like going to send an electronic message across like a telegram machine, right? So like Morse code, similar to that. But it's going to come back as like garbage, right? So unless I have the exact same settings on both machines, right? So the interesting thing is when we thought about the alphabet shift cipher, we only had like 20 permutations. There was only like 20 different ways that we could look at how that was going to be kind of jumbled up, right? Well, now with this machine, this is the number, right? This is a big ass number. If you look at this number, it's huge. It's a massive number of possible states that are possible for the encryption to be, right? So in order for the key or the setup or the state of the decryption machine and the encryption machine, it has a lot of different states that are possible that are required to be identical on both sides in order for this machine to work. And so if the Germans wanted to simply make it completely impossible for us to decode anything, all they had to do is just change a little bit of a thing on the machine and not tell us what they changed, and then that would make it impossible for us to kind of figure it out. So what had to happen is there had to be a way to kind of figure out how we could kind of come up with a way of how this thing might be doing something. And so what happened is there was these wonderful cryptographers, probably the first group of cryptographers, the founders of cryptology, were in a place called Bletchely Park. And there was a lot of really great cryptographers there. There was a lot of guys that were there that were really great at doing crossword puzzles. There was females there. There was males there. There was no care, because it was World War II and they were fighting the Germans. They were attacking and bombing and bombing London constantly, and they were attacking their ships, and the Navy was sinking their ships, the German U-boats, and so they needed to fix this problem, and it was a genuine problem. They didn't care. They just wanted to get the best minds together. They didn't care about if they were eccentric. They didn't care if they were kind of weird. They didn't care if they were kind of off the wall or whatever, and so they got all these guys together and they came up this place in Bletchley Park, and they figured out a way to fix the problem, right? Now there was a little bit of human engineering in here, so they knew a little bit of the code. They kind of knew a little way to kind of like shave down what to check for. But what they were able to do is they were able to kind of use a system of just checking this, checking this, checking this, checking this, checking this, using what Alan Turing was called a Turing complete machine. And he actually wrote this paper back in 1936, and I kind of cite this here. But in essence, what it was is it gave them the ability to kind of figure out and decipher part of the Enigma code. And so it was interesting because if they were to act on certain things and they were to reveal that they knew some of these things, they could have taken action and saved lives, but then they could have revealed to the Germans that they actually knew the code. So there was a big dilemma between a mental and moral dilemma on whether to take action on certain things, because it may only save a couple of the lives, whereas it might cause the compromisation or be compromising the code itself, and it would cause all of the work to be wasted of the hackers and the crackers. So all they would have to do is just make a small change to their Enigma machine, as we said before, and it would just cause just complete havoc and make them have to come back to zero and start over. So we didn't want that to happen. So there was a lot of really weird politics that was going involved here. And then there was also this gentleman by the name of Alan Turing. As I mentioned before, he kind of gives birth to modern computing. He gave wrote one of the most influential papers on computing back in 1936, before we even knew what a computer was. And when he was talking about computing, he was actually just talking about how you could use simple math in order to find out and go through a series of checks and balances to find out whether or not something was true or not. And not only math, but also binaries, just ones and zeros. So in essence, he created this really crazy looking machine that had like these tape, and it had like this eye that would look and see if it was a 1 or a 0. And then that machine could, in essence, compute any problem that you might have. And so really interesting paper. I encourage you to go out and take a look at it. But Alan Turing, in and of himself, was an amazing individual. Really had kind of an interesting life. Let's talk about that real quick. I like talking about this politics stuff so because it really shows how we've progressed as a society, and also how we've been able to kind of adapt some of this wonderful technology. So I do want to talk about Alan Turing a little bit further here. Alan Turing was a war hero. I mean, he cracked the Enigma code. He was genuinely responsible for much of the things that happened at Bletchley Park, based on some of the abilities that he was able and thoughts that he was able to come up with. Now, he was a hero, but memory is short-lived. Shortly after World War II, even though he was a war hero, all of his work was secret and not allowed for public eye. And so therefore, most did not know of his work, and he needed to keep that a secret. Not only that, he needed to keep his public life, private life, a secret as well, because Mr. Turing was homosexual. And so because of that, they gave him chemical castration, which caused mental damage, and he committed suicide 2 years after he was punished for not actually, he was given a choice of going to jail or taking the chemical castration, and he chose the chemical castration, which in turn, in essence, basically made him quite suicidal. He soaked a apple in cyanide, much like Snow White, and ate the apple and died. And so Mr. Turing was a war hero. He was a brilliant mind, gave rise to modern computing, and anyone that works in computing should take their hat off to him, and he is a great, great man. In 2009, Gordon Brown, the British Prime Minister, actually said to Mr. Turing and his family, "We are so sorry. You deserve so much better." And I couldn't agree more. So anyway, that's Mr. Turing's story. What a great story, huh? So modern cryptography. Let's talk about modern cryptography. It is really the cornerstone of what we consider secure communication today. So when you think about setting up a secured channel with your bank, or you think about using some type of secured method of communication, you're probably using some type of modern cryptography. And so we need to understand some of the key foundations of modern cryptography and the various concepts that are used in modern cryptography, and talk about some of the computational and complexity theory that's used, and also some of the probability theory, maybe even some of the number theory that might be used. We'll talk a little bit about that, but really what we need to understand is that modern cryptography is really a lot of math. It's a lot of math that's used in order to be able to figure out problems, and based on that Turing complete machine, similar to what we talked about earlier. So to understand modern cryptography, you need to understand the terms that are used in modern cryptography. The first term is encryption. And so we know encryption as what we've heard already is simply the ability for us to take data, cipher something, and then make it unreadable. And so we're going to talk about that. We're also going to talk about hashing in a digest, as well as symmetric encryption and asymmetric encryption, and kind of talk about what the differences are between those two. And so it's a little bit to cover here, but hopefully I will keep this high level enough so that everybody can understand it and keep a good grip on everything that we're talking about. So again, as we know, encryption is just simply the ability for us to take information and convert that information into data or into a code to prevent unauthorized access to that data. When we do that, that's called encrypting the data or ciphering the data. When we use some method to read the data, once we're ready to read it again, once it's been encrypted, we need to decrypt the data. That's called deciphering the data. Pretty simple. Hashing. When we think about hashing, hashing is a little bit different than encrypting or ciphering, in that a hash actually takes a non-standard set of data and creates a standard set of output. Let me explain to you what that means. So imagine, if you will, remember we talked about hash, corned beef hash earlier, and we said that corned beef hash basically just takes corned beef and meat, mixes it all together, and gives us an output, right? So if I was to go get a cup of that corned beef hash, it would be the same as if I was to go get the first cup, would be the same probably as the sixth cup. It's pretty much the same content, right? So the content of the output is standard, or a standard set of output. And actually it's just called a digest is what is considered to be the output. And so the input is just simply the the data that's coming in, and then the hashing method is the math that's being used to scramble or jumble that data so that it's you're not able to read it as it was initially inputted as, right? So you can't easily create the output. We can't easily take the output and use the output to create the input. Okay, so the input produces the output or the digest, but you can't go backwards. And so it is what we call collision resistant. Also, in that two different inputs, one small change to the input. So let's say if you have 2 terabytes of data and you just change one space on one character on one document, then that will produce a completely different hashed output. And so what that does is it makes it very collision resistant. And it makes the information look completely random. As a matter of fact, let's take a look here. And so, well, before I get too far ahead of myself, before I show you this little quick demo, let's kind of summarize what we're saying. So a hash function is just simply taking any type of input or any string of input or any length of input, anything, any input, okay? And then it's going to produce a fixed length output. So it's going to produce a standard output. Maybe it's only 8 characters. Maybe it's 32 characters, right? But that output is going to be the same regardless of what was put in. So if you put 1 character in or if you put 2 terabytes of characters in, you're still going to have the same output. That's very important. So in that way, the person knowing the hash value is unable to know the original message, but only the person who knows the original message can prove the hash value is created from that message. So hopefully that makes sense. All right. Okay, so let's take a look at it. And so if I was looking at a hash function, and I was thinking about a hash function, and if I was looking at just simply the word fox as an input, then as I said before, we have the hash function that actually scrambles the data, right? It's just running through this math, right? And it's producing this output. Well, fox isn't very much, but look at the standard size output. Remember, the digest is a standard size output. So regardless of what's put in, the output is still the same size, right? So that's important. And so then, in addition to remember here is that if I just make one small change, so look here, the only thing that I've changed is the word over. So notice here I spelled it correctly. Here I spelled it with a U. Here I spelled it with a typo. Here I missed the V. And regardless of the minor flux of change to the word over, the major change to the digest or the output is majorly different. That's pretty important, right? And so that's the important thing to remember about a hash, because a hash is going to be used really throughout throughout all cryptographic functions. And so it's really one of the foundational sets of knowledge that you need to understand in order to understand blockchain cryptography or anything that we talk about here forward. So with this technology, what are some things that we've seen? What are some advantages that you see from this? Well, if you've ever noticed, sometimes you might talk to a network administrator at your work, and they might say, hey, we have single sign-on, and that just means that your password never gets sent across the wire. And you think to yourself, but I typed my password in, how did it never get sent across the wire? Well, it never gets sent across the wire because what we're using is a series of what we call zero-knowledge proofs and challenging and handshakes. But in essence, what we're doing is we're challenging you to see if you know something, and then you show that you know something, and then we know that you have a certain set of knowledge based on this. And so now we have the ability to give you access to something. And so that has been used throughout the history of validating your user IDs and passwords, and single sign-on, and Kerberos, and all of these various different authentication methods use this handshake authentication, and that's kind of what we're doing there. So also anti-tampering, if we think about anti-tampering, obviously if we know that if I run something through a hash and I then sign something and say that, hey, I haven't talked about signatures yet, but if I run something through a hash, then I know that it's a particular output, and I then say that, hey, this is the input that I put in, and this is the output that you're putting out, so this is the hashed signature of this input, right? Then I can ensure the validity of the input data, right? So then if I create an image, let's say, for instance, as a software company, of my, let's say a VMware image of my stack, and I load it up into a VMware image, and then you push up that stack and you load up that image, then you want to make sure that that image doesn't have any malicious code in there. You want to make sure that it came from me. You want to make sure that it's the code that you downloaded from my GitHub repository. You want to validate that code so you can then use that digest in order to, or that signature in order to validate the file that you just downloaded. So that if there was a spoofing attack, or what we call a man in the middle, then you would ensure that that person didn't like steal your stuff and then maybe stick some code in there and then send it back to you, right? So we want to make sure that doesn't happen. Then you also have digital signatures. So we'll talk about that now, but I'm going to talk about it in a second, but I want to kind of introduce you to digital signatures. But what that does is, now that we know that we can create a hash creates a certain digest, then when you start to think about this public key, private key, and I'm going to talk about that in a second, but what it is it's just hashing that can only go back to the original source. So keep that in mind when we think about public keys and private keys here in just a second, because that's going to be really important. Okay, so now that we understand what a hash is, right? So that means that if we're using the same key and the same hashing algorithm to kind of like scramble that data, and we're using the same math equation, but we're changing the variables within that equation using a key, then we can scramble the data differently because we would have to know what the key is, right? So that would mean that the key in and of itself would have to be shared between two parties. So here, the originator or the source of the key would have to share that key with the person that they want to share the data to, and then those two individuals would have to be responsible for the security of that key. And if that security was ever compromised, then therefore the data could be compromised. And so in symmetric encryption, we use the same key for the encryption of the data as for the decryption of the data, and therefore there is an inherent problem with that, which we saw with the fall of the German Enigma machine, because they were able to crack that code. So with asymmetric encryption, the encryption works a little bit differently. Here what we have is we have a public key. It goes through and it uses a different key that is actually a hash of the private keys. So if you think about public keys and private keys, remember that if you don't know the input, then you can't know the output, right? So when you think about what is a public key is just a hash of a private key. And then if you hash it again, then that's an address, and so that's kind of how that works. And so with asymmetric encryption, we're just using that hashing function in order to generate the keys so that we have unique identity in identifying that I own something, or I own the private key that's associated with a particular public key. So there's a unique relationship between public keys and private keys that give them the ability to have what we call collision resistance, and also to ensure authenticity of the owner of a particular public key's private key, and things like that. So this allows us to do secure communication with what we call secure envelopes. It also allows us to do secure authenticity with secured signatures. And there's all kinds of really cool stuff that we can do here. And then also, in addition to that, we can also take these hashing algorithms that we're talking about and we can kind of chain them together so that unless you know the chain or the order of the hashing algorithms, then you're really not going to be able to kind of figure out what it is that somebody's doing. So anyway, there's a lot of really cool shit here. Wow, I probably shouldn't have said that word, but anyway, there's a lot of cool stuff. I hope you guys get a lot of value out of this. I mean, anyway, I'm just trying to put all this tech together for you so that you understand encryption so you guys can start building real-world solutions, because that's ultimately what we want to do, right? So now that we've learned all this stuff, what are some things that we can do? You know, I kind of mentioned some of these already, but, you know, authenticity of data, obviously that you have a particular identity that's associated with the public key, you know, that's very important. So, you know, if you publish that, hey, this is my public key, then you can say, hey, there's a private key that's associated with it. So it's proof, it gives a certain level of proof of ownership. And so there's different methods that you can kind of enforce that. But anyway, it gives you kind of the idea to figure that out. With that being said, if we have an immutable ledger that we've kind of talked about already, then now I can put digital ownership on that immutable ledger for any object that I want to own, whether that be a medical record, whether that be a piece of property, whether that be my self-sovereign identity, whether that be auditing information about my company that I just simply want to be out there that ensures that I didn't change anything. You know, maybe a hash of my backup to ensure that this was a state of the data at a particular time so that I ensure that nobody's tampering and, you know, messing with the data that we have in our data center. You know, there's all kinds of really cool stuff that you guys can do with this cryptographic technology that's, you know, just in your toolbox. So anyway, that's what we're using this for. It also gives you the ability to do secure transfer of assets. And we're seeing that with a lot of blockchain technologies, a lot of white papers that are coming about. And then also the data can be hashed using, you know, like I said earlier, a chain of encryption and hashing methods. So that's another layer of encryption that you can put on top of this. So in future videos, you know, I'm going to get back into blockchain tech. I'll talk about scaling. I'll talk about some of the problems that we run into when we think about scaling. I'll talk about layering solutions. Talk about public and private chains. I need to get into that. Permission and non-permission networks. And so anyway, that's pretty much all I have for you. Hopefully I didn't go too long for you guys today. Again, I hope you enjoyed it. Basic introduction to cryptography. We talked about hashes. We talked about ciphers. We talked about Bletchely Park. We talked about Enigma machines, Alan Turing, symmetric and asymmetric encryption. And so, man, I hope you guys are digging this stuff. I'm getting a lot of good positive feedback, so hopefully everybody's enjoying it. I know I made a couple of mistakes here and there, you know, mostly just little words mistakes that I kind of messed up on. But anyway, we'll figure it out. We'll get through all this. Again, here's my Ether address, my email address, No Magic Just Logic, Tommy Cooksey. I hope you enjoyed the videos, man. Please reach out to me if you need anything. And let's take advantage of this trust revolution that we're coming upon. Thanks, guys, and have a great day.